Section 16.6 Weak Acids. Most acidic substances are weak acids and therefore only partially ionized in aqueous solution. We can use the equilibrium constant for the ionization reaction to express the extent to which a weak acid ionizes. If we represent the general weak acid as HA, we can write the equation for its ionization reaction in either of the following ways, depending on whether the hydrated proton is the recipient as a hydronium or as a proton. Because water is the solvent, it is omitted from the equilibrium constant expression. Thus, we can write the equilibrium constant expression as either K sub C as equals the hydronium concentration times the conjugate base concentration over the acid concentration, or as a proton concentration times the weak acid conjugate base concentration over the acidic concentration. We did this for ion product constant for ionization of water. We changed the subscript of the equilibrium constant to indicate the type of equation to which it corresponds. The subscript on K sub A denotes that it's an equilibrium constant for the ionization of an acid. So K sub A is called the acid dissociation constant. Table 16.2 shows the names, structures, and K sub A values for several weak acids. Appendix D provides a more complete list. Many weak acids are organic compounds composed entirely of carbon, hydrogen, and oxygen. These compounds usually contain some hydrogen atoms bonded to carbon atoms and some bonded to oxygen atoms. In most all cases, the hydrogen atoms bonded to the carbon do not ionize in water. Instead, the acidic behavior of these compounds is due to the hydrogen atoms attached to their oxygen atoms. The magnitude of K sub A indicates the tendency of the acid to ionize in water. The larger the value of K sub A, the stronger the acid. Hydrofluoric acid, HF, for example, is the strongest acid listed in Table 16.2, and phenol is the weakest. Notice that K sub A is typically less than 10 to the negative 3. Calculating K sub A from pH. In order to calculate either the K sub A value for a weak acid or the pH of its solutions, we will use many of the skills for solving equilibrium problems that we developed in Section 15.5. In many cases, the small magnitude of K sub A allows us to use approximations to simplify the problem. In doing these calculations, it's important to realize that proton transfer reactions are generally very rapid. As a result, the measured or calculated pH for a weak acid always represents an equilibrium condition. Percent ionization. We have seen that the magnitude of K sub A indicates the strength of a weak acid. Another measure of the acidic strength is the percent ionization, which is defined as percent ionization equals the concentration of ionized over the original concentration times 100%. The stronger the acid, the greater the percent ionization. For any acid, the concentration of acid that undergoes ionization equals the concentration of proton that forms, assuming that the ionization of water is negligible. Thus, the percent ionization of acid HA is given by percent of proton at equilibrium over HA initial times 100%. For example, 0.03 molar solution of nitric acid contains 3.7 times 10 to the negative 3 molar of protons. Thus, the percent ionization is 11%. Using K sub A to calculate pH. Knowing the value of K sub A and the initial concentration of a weak acid, we can calculate the concentration of protons in a solution of a weak acid. Let's calculate the pH of a 0.3 molar acetic acid, the weak acid responsible for the characteristic odor and acidity of vinegar at 25 Celsius. Our first step is to write the ionization equivalent for the equilibrium for acetic acid. Notice the hydrogen that ionizes is the one attached to the oxygen atom. The second step is to write the equilibrium constant expression and the value for the equilibrium constant. From Table 16.2, we have K sub A equals 1.8 times 10 to the negative 5. Thus, we can write K sub A equals 1.8 times 10 to the negative 5. As a third step, we need to express the concentrations that are involved in the equilibrium reaction. This can be done with a little accounting, as described in sample exercise 16.10. Because we want to find the equilibrium value for the proton concentration, let's call this quantity X. The concentration of acetic acid before any of it ionizes is 0.3 molar. The chemical equation tells us that for each molecule of acetic acid that ionizes, one proton and one acetate ion are formed. Consequently, if X moles per liter of hydrogen or proton form at equilibrium, X moles per liter of acetate must also form, and X moles of liter of acetic acid must be ionized. This gives rise to the following table with the equilibrium concentration shown on the last line. As the fourth step of the problem, we need to substitute the equilibrium concentrations into the equilibrium constant expression. The substitutions give the following equation. K sub A equals X times X over 0.30 minus X equals 1.8 times 10 to the negative 5. This expression leads to a quadratic equation in X, which we can solve by using the equation solving calculator or by using the quadratic formula. We can also simplify the problem, however, by noting that the value of K sub A is quite small. As a result, we anticipate that the equilibrium will lie far to the left and that X will be very small compared to the initial concentration of acetic acid. Thus, we will assume that X is negligible compared to 0.3, and so 0.30 minus X is essentially equal to 0.3. As we'll see, we can and should check the validity of the assumption when we finish the problem. By using this assumption, equation 16.3 now becomes K sub A equals X squared over 0.3 equals 1.8 times 10 to the negative 5, which gives you an X of 2.3 times 10 to the negative 3. The concentration of X is 2.3 times 10 to the minus 3, and the pH of negative log of 2.3 times 10 to the negative 3 is 2.64. We should now go back and check the validity of our simplifying assumption that 0.3 minus X equals 0.3. The value of X determines is so small that for this number of significant figures, the assumption is entirely valid. We are thus satisfied by the assumption to be a reasonable one to make. Because X represents moles per liter of acetic acid that ionize, we see that in this particular case, less than 1% of the acetic acid molecules ionize. Percent ionization is 0.77%. As a general rule, if the quantity of X is more than 5% of the initial value, it's better to do the quadratic formula. You should always check the validity of any simplifying assumptions after you finish solving a problem. Finally, we can compare the pH value of this weak acid to a solution of strong acid of the same concentration. The pH of the 0.3 molar solution of acetic acid is 2.64. By comparison, the pH of a 0.3 molar of strong acid, such as hydrochloric acid, is 0.52. As expected, the pH of the solution of weak acid is higher than that of the solution of the strong acid of the same molarity. The properties of the acid solution that relate directly to the concentration of proton, such as electrical conductivity and the rate of reaction with an active metal, are much less evident for the solution of a weak acid than for a solution of a strong acid of the same concentration. Figure 16.8 represents an experiment that demonstrates the difference of comparing the behavior of acetic acid and 1 molar hydrochloric acid. The 1 molar acetic acid contains only 0.004 molar protons, whereas 1 molar hydrochloric acid contains 1 mole of protons. As a result, the rate of reaction in which the metal is much faster than for the solution of hydrochloric acid. As the concentration of weak acid increases, the equilibrium concentration of proton increases as expected. However, as shown in figure 16.9, the percent ionization decreases as concentration increases. Thus, the concentration of proton is not directly proportional to the concentration of the weak acid. For example, doubling the concentration of weak acid does not double the concentration of proton. The lack of proportionality between the concentration of a weak acid and the concentration of proton is demonstrated in sample exercise 1613. Polyprotic acids. Many acids have more than one ionizable hydrogen atom. These acids are known as polyprotic acids. For example, each of the hydrogen atoms in sulfurous acid ionize in successive steps. The acid dissociation constants for these equilibria are labeled Ka sub 1, Ka sub 2. The numbers on these constants refer to the particular proton of that acid that's ionizing. Thus, Ka2 is always refers to the equilibrium involved removal of the second proton of a polyprotic acid. In the preceding example, Ka sub 2 is much smaller than Ka sub 1 because the electrostatic attractions we would expect a positively charged proton to be lost more readily from the neutral hydrogen sulfate molecule than from the negatively charged bisulfate molecule. This observation is general. It's always easier to remove the first proton from a polyprotic acid than to remove the second. Similarly, for an acid with 3 ionizable protons, it's easier to remove the second proton than the third. Thus, the K sub A values become successively smaller as successive protons are removed. Sulfuric acid is a strong acid with respect to the removal of the first proton. Thus, the reaction for the first ionization step lies completely to the right. Bisulfate, on the other hand, is a weak acid for which Ka sub 2 is 1.2 times 10 to the negative 2. Because Ka sub 1 is much larger than the subsequent dissociation constants for the polyprotic acids, most of the proton in the solution comes from the first ionization reaction. As long as successive Ka sub values differ by a factor of 10 to the 3 or more, it's possible to obtain satisfactory estimate of the pH of polyprotic acid solutions by treating them as if they were monoprotic acids, considering only Ka sub 1.